course, I didn't want to get myself stuck. No. Just thought I wasn't sure this information. This one's.
Whoa. Yeah.
It's really good. This one worked great. Oh wait, is it the thing on the left? It's gotta be this thing here that has a picture of that on it.
Yeah, I think it's not that.
I don't know if you push it down, pull it up, pull it out, push it in. So if you look at it, it's this thing. There are other places. No, Mark got back to me already. Really? Doesn't seem like Mark. Basically what I'm saying.
Yeah, go for it. Yeah, I mean, you get first bet or second. Yeah. You pick early. Yeah, no, Nick, we already got some. You're good.
Yo, is Tariks recording?
I think he's putting it on YouTube. It's like a live
Oh, that's
stream.
right, he did that link out.
Yeah.
I'll use this organization for like 5 months. It's not even the real one.
Before. Those damn Macs. 30 every time.
If they're reserved, does that mean that we're supposed to sit in the front row?
I assume the committee's gonna sit right here.
There are only 3 committee members, so as long as there are 3 empty seats.
That's where it's at.
I know.
Only three faculty members. You're gonna have to grant them, so. Tariks said it was okay. That was wondering if students are allowed to sit up front.
We don't have a lot of seats, so yeah, it's like it's
My
like
answer
wherever
was
you'd
you
like.
said it was okay.
But these 3 here will probably be the committee. Yeah, I'm actually live streaming. Yeah, but I'll leave it there.
have a grad student file naming structure? I was gonna say, he doesn't have at least one file that ends in underscore old somewhere on his desktop.
Oh, yeah, my first mistake was even letting me see my desk.
It's probably smart.
Right snack in front of
Yeah, I mean, there's an empty seat in the center. It's all yours today.
Like 2 committee members, you and another committee member.
I think that is an excellent.
Who's on the committee?
Mark, Dan, Kodashek, Cindy, and Hadas.
So that's being Skyped in, is that what that is?
Yeah. So that's for Hadas, and then the phone's for live stream.
Oh, yeah. You said stores that have the evening donut, I was like, where? I'm like, oh, is that? Right.
Trying to like move things precise amounts, certain number of pixels. I don't know.
Go on the thing and tell it exactly what pixel you want everything to
It's
do.
entirely possible that I just don't have the learning curve to the level that it needs to be.
That is awesome.
But the learning curve for programming something and seeing it appear immediately. Let's see.
It's also weird to do.
Hey. Pretty good?
Probably don't like
Yeah, lots of donuts. Coffee too. Do you want coffee?
Is it doesn't?
She's about to call in when she's finishing up the meeting. How are you?
Good.
like you do. As a complication. Yeah.
No, I did that yesterday. One thing out of the one day, one email a day.
Curiosity, I'm not super fast. To be fair, like, when I work.
Visual.
Like, how do I know to do it?
Supposed to be really good.
Hmm? Yeah. Only the best for you guys. It's also right in your dad's apartment, so I mean.
It's right underneath my apartment. Right? But I don't remember there being a pond there.
I said the same thing, but I had this slash.
Yeah. I don't remember there being a pond. This seems bigger than it was. No, they're on this bridge.
Yeah.
Yeah.
You can just say like, sorry. I talked to you. It's aiming for 50 minutes.
It is difficult.
That's my defense.
That's what, yeah, that's what it's like. And it's not standardized play, it's not pattern.
Dan and Hadas asked me to call her in a few minutes.
No. I could sit. No. We have
Well,
I can.
don't you work here? What are you doing here? I mean, you brought somebody with you, so yeah.
Can be before me. Whatever. He already came already. My show.
Yeah, Pickles, you should be sitting up front during my time.
Don't trip on me.
Hey, can I get that? Lincoln High School. I know. Don't ask that.
He didn't talk with me at all, but I assumed it was going to happen. Did I need to arrange that?
No.
Yeah, that's a good idea. Yeah.
I sat there like.
Apparently Hadass is still in a meeting.
Okay.
Yeah. Is any of this stuff in your way, or?
They did it at some point last year.
Yeah, it's all good. I'm just waiting for Hadass. Just like the committee spot.
We only have one more.
Everyone who can conceivably be here is here. The only person I'm waiting as a surprise guest is John Greco.
Exactly. That would be really good.
John Greco was in.
Yeah. I think a few people are watching on the live stream, so maybe he's there.
I can see it.
Hey, Hadass.
Yeah, let me move my laptop as usual. The sun, Ithaca, serving us.
It's okay. Wouldn't be really be a mod ASL telecon if I could see you. You know.
Hey, I'm embracing my factor's son. You know, I'm not going to see you for a while. Oh, okay, you good?
Okay. Yep. Yeah. All good. And so this really is maybe the last telecon, because even though you can't see Jim and Jonathan, they're probably watching on the live stream. I can't really tell, but they're probably there.
Oh, June Johnson are there?
No, they're watching on YouTube. I'm streaming it. Yeah. Can you hear okay?
I can hear.
Okay,
I
good.
can hear totally fine. Let me download your
Yeah.
slide.
So let me see if I can turn you around here. So Cindy and Mark are here.
Yeah, let me see.
Yep.
Hey, how are you? Oh, wow, a lot of people. Okay, you're just totally silly right now. Thanks for the heads up there.
Yeah, there's a big crowd.
Yep. And we're still waiting on Dan K, but he should be here any minute.
I believe that was the situation last time too.
sure you can see.
So are you gonna be sharing your screen or no? Do you want me to look at the slides?
Yeah, so I put the slides in Dropbox. There's the actual PowerPoint or the PDF, which is much smaller, if you want to download that.
Yeah, I don't really want to download 660.
Yeah, I figured.
Okay, let me see if I can save it to the folder.
I've never had that situation. Yeah, it's okay. Usually
So, Mark, did you check with Peter? Yeah, we're all good. Medium conference series you going?
no, not a different place.
Ah, okay. So just let Alexander and Devin know because they'll lead. Or I guess you can know.
What's up?
I was just talking about the thing afterwards.
Oh,
It's in a different place.
yeah.
So I can.
Mark, is that slide white or is it?
It's pretty white. It might be a.
Can you move to a slide that I want to see if I can see it.
Sure, yeah.
Okay, I'll download it. Fine.
Okay.
I know it's PDF.
Yeah, the PDF's fine. You've already seen the videos, so.
No new videos?
What? Oh, there are new videos, but you've seen most of the videos. Come on, of course there's new videos.
Yeah, fine. I'll download the whole thing.
While we're waiting for the last thesis committee member to arrive, thought I could just make a couple announcements. At 4:30, so 2 hours from now, we will have the post-defense. I don't know what we don't usually call it celebration because we don't know what's going to happen. But the post-defense gathering, it'll be in Skirkanich 508. So if you're a guest here, ask one of the students. Skirkanich 508 is around the corner. This is Tarik Tosun's defense. In case you don't know. Quick introduction. Tarik came here, 6 years ago?
6 years ago.
6 years ago.
2012.
From Princeton, where he did his undergrad. We were pretty excited to have him here. I was pretty excited. He actually wanted to focus on a research area that I had always wanted to go into, which was this, like, how do you describe tasks for a modular reconfigurable robot that can take any shape? Turns out that it's a really, really hard problem. And so he kind of pivoted away from that, which is a smart thing to do. One of the interesting things about Tarik, that I think is really valuable, he was able to kind of compartmentalize his work and his non-work time, I believe, because his now fiancée lived, was in New York, right? So it was making sure that he could be very productive during the time that he was here, and then during the weekends he was not. I was super impressed. So actually, in my group meeting tomorrow with my PhD students, I've asked him to give hints to everybody else, especially the junior ones. How do you do that? Because it's not an easy thing. So anyway, that's a quick introduction. Cindy, you want to give some rules about what we're doing?
Sure. So for this defense, Tarik is going to give a talk. It's going to be about
55.
It's going to be about 50 to 55 minutes. Then we'll open it up to questions from the audience, and then we'll kick everybody out, and then the committee will have a chance to grill Tarik in more detail, and then come together to a decision. Right? So does that sound good? All right, so take it away.
All right. Well, thank you all so much for coming. Really appreciate you being here for my defense. The title of my talk is Reconfigurable Robots, Systems that Transform Themselves and Their Environments. So, of course, my primary research interest is robotics. And one of the most challenging problems in robotics today is building robots that can really operate in the wild. So outside of factories, outside of labs, in our wider world. And operating in our world requires a broad range of physical capabilities, whether we want robots to operate in a really messy scenario like a disaster response kind of scenario, or even just navigating and traversing our complicated indoor environments in our homes. So most of my research focuses on modular reconfigurable robots. These are systems that are composed of repeated units that are themselves robots called modules that can connect together to form larger structures. And by changing their connective structure, they can form different configurations with different capabilities. The idea is that these systems can be very, very flexible. So these systems have been studied since the early 90s, and a lot of the existing work in this area has focused on basically establishing the fundamental capabilities that really differentiate these systems from traditional robots. So of course we've seen lots of hardware systems that are capable of self-reconfiguration, actually changing into different forms. We've seen, in terms of control, a lot of work in distributed algorithms for emergent behaviors from the inherently distributed clusters of modular robots, things like reconfiguration planning, and of course, plenty of examples of these systems exhibiting interesting morphologies and behaviors. But what we've really wanted for these systems since the very beginning is a reactive autonomous reconfiguration in unknown environments. The idea that we could send a modular robot into an unknown environment and have it autonomously and automatically select the right body shape that it should take on and reconfigure to that shape in order to access the capabilities it needs to complete its task. My research has taken the next steps to really achieve this capability. I've done research developing hardware that's capable of robust, rapid reconfiguration, theory linking tasks to robots and behaviors that can accomplish them, and integrated systems that actually let us do this all autonomously. So more recently, I've also started thinking about reconfiguration from a slightly different perspective. So where self-reconfiguration is the robot basically changing its own body to suit the needs of its current task and environment. Environment augmentation involves robots kind of reconfiguring their environments, actually changing their environment in ways that make it work better for them. And I've started to actually explore this idea with my modular robots, having them build structures that allow them to overcome obstacles in their environments. So in my talk today, in the first part, I'm going to focus on modular reconfigurable systems, and I'm going to kind of build up from hardware design to algorithms and frameworks that allow us to address tasks, and finally talk about a system that my collaborators and I have created that allows these robots to accomplish tasks autonomously. And in the second part, I'm going to talk about environment augmentation and show you how introducing the capability to build structures makes our modular robots more powerful, and then close by presenting an algorithm, some theoretical work that actually lets us figure out what structures the robots should build to gain the most advantage in a new environment. So let's start with the hardware. So this is S'mores EP. I actually have a couple of these robot modules here with me. This is basically the core hardware platform of my research. These robots have 4 degrees of freedom. They've got 2 wheels that allow them to each drive independently, kind of like a car, as well as a pan and tilt degrees of freedom in the middle. They're individually mobile, right? They can operate on their own or as a cluster, and they connect together using a magnetic connector that lets them form larger structures. We built 25 of these modules. They're all identical. We built them right here at Penn in the engineering building in the old mod lab. And importantly, they have no sensors that let them gather information about the world around them. So I'm actually going to pass around one of these modules. So quite a bit of work went into actually designing and building this robot. But I'm going to highlight one of the kind of core technologies that we had to develop to make this system work, and that's the connector, which we call the EP face. So the EP face is an array of 4 electropermanent magnets arranged in a ring in a planar face, and that makes it symmetric. So if you take any face of one module, it can connect to a face of another module, any other face, in one of 4 kind of angular positions. The connector is strong, fast, and low energy, and a lot of that has to do with the fact that we're using electropermanent magnets for connection, which I'm also going to pass around. So electropermanent magnets are solid-state magnetic devices whose magnetic field and therefore force can be turned on or off using a pulse of current. So basically the way this works, and I'm actually passing around a couple magnets for you to handle as well as an EP face. The way this works is there's kind of 2 components to these EP magnets. It's an electromagnet coil with a permanent magnet core. So this is the magnet before it's been wound, and this is after we've wound the coil around it. And in the core, there's 2 kinds of permanent magnets. There's an Alnico rod magnet and a neodymium rod magnet. And when these rod magnets are magnetized fully, they have the same magnetic field strength, so they're the same strength of magnet. The difference is that Alnico magnets have a lower magnetic coercivity than neodymium. That means that in the presence of an external magnetic field, it's easier to get an Alnico magnet to repolarize, actually flip poles. So what we do is we actually generate a field, an external field, using the electromagnet coil by pulsing a high current through it for a very short amount of time. And that field is strong enough that it actually repolarizes the alnico magnet, but leaves the neodymium magnet unaffected. So when the magnets are in phase, so north-north, south-south, they act together basically as one magnet, and the force is turned on. Right? When we repolarize the alnico magnet so that it's out of phase with the neodymium magnet, they oppose each other. In that case, they basically kind of cancel each other out. Right? So no magnetic field exits the EP magnet, and the magnetic force is turned off. So this is a really fast and energy efficient process, which is great if you're going to use this as a connector for a tiny robot that has small batteries, right? The switching time for a single magnet is 20 milliseconds. And since we do them in series in each face, it takes 80 milliseconds to switch an entire face. And requires only 2.5 joules, which is 1/10,000th of the s'more's battery life. So from the perspective of energy and time, we treat connection and disconnection for this robot as a basically free operation, which is really nice. We've done some work to characterize this connector. So we've compared it to quite a few other connectors for modular robots from the literature, which this table kind of shows. I'm not going to go into too much detail on that, but I'll highlight kind of two really important metrics here. So the first, of course, is strength. Of course, we want the connection between modules to be strong. We do pretty well there with the EP face. We can support almost 90 newtons in tension on average. That's the weight of 20 modules if I was holding them kind of straight up like this against gravity. But actually a more important metric of performance in terms of strength for the robot is the characteristic strength. This is basically the number of modules that the connector can support in cantilever, so straight out against gravity like an arm. We can support 3.1 modules, and this is very important, obviously, if we want to use the robot for tasks. This kind of determines the workspace of an arm or a leg we could form, and often the amount of work we can do on the environment in terms of lifting things. Another really important metric is area of acceptance. So this basically measures the kind of tolerance to slop or uncertainty that the connector can kind of operate under. So the nice thing about using this kind of flat magnetic surface to connect is that it's actually very tolerant to kind of disturbance, right? So the modules will actually pull themselves together from a distance of 4 millimeters normal to the face, or 7 millimeters parallel to the face, and successfully connect. So this kind of forgiving connection is really useful if you're trying to do autonomous reconfiguration of these robots with noisy sensing and potentially unknown environments, that kind of thing. Okay, so now I want to move on to our work in frameworks and algorithms for addressing tasks with these robots. So sort of at the very highest level of decision making, right? If you want to get a task done with these robots, you've got an additional step of reasoning that you and planning that you need to do compared to a traditional robot. Not only do you need to decide what the robot's going to do to complete the task, but also what the robot's going to be. And that has implications for basically everything else you're going to do, right? Planning, control, sensing, all of these things. So this is a challenging problem. And what we'd really like to be able to do with these robots is have them address high-level, complex, multi-part tasks, where they might need to actually reconfigure multiple times in order to access different capabilities of different morphologies, right? So this is an example of the kind of task we might want to attempt with these robots. We want the robot to climb up on top of a table, explore around, and respond appropriately to some objects that it might find. So in this project, this is a collaboration with Professor Hadas Kreskazit's group at Cornell, including especially Jim Jing, who's my co-author on the paper. And we've actually developed a system that lets us do this with the robots. Our framework includes 4 components. We have a design and simulation tool, a library of robot designs, high-level mission planner, and of course, modular robot hardware. And I'm going to touch on each of these briefly and then show you how they all connect to actually let us accomplish tasks. So our design and simulation tool is called VSpark. This tool was developed by recently Dr. Jim Jing at Cornell. Jim, if you're watching, that's your shout out. So this is a really great tool that lets us actually develop new configurations and behaviors for the robot that populate our library, right? So users can basically kind of snap together modules and create behaviors and simulate them. And anything that you do in the simulator can actually be saved to a server, which is then accessible by other people who use the simulator and also becomes part of our design library. And actually this tool is available at www.vspark.org. It's free and available for any operating system. You can go start playing with it now if you're bored with my talk. Using that simulator, we're able to basically populate our library of designs. So this is kind of a collection of configurations and behaviors that kind of encodes the functionality, the total functionality of the robot, right? So our library right now has about 50 configurations and order of 100 behaviors in it. And basically a library entry consists of a configuration behavior pair labeled with properties that pretty much describe the constraints of the environment under which it can operate, as well as the desired outcome of the behavior. So to give you an example, this library entry would be, the configuration is a snake with 7 modules, the behavior is a climbing behavior, and the environment properties that we've labeled this with are a stair height between 2 and 3 modules high, that's where this behavior can operate, and the behavior properties are the action is climb, and the speed is 1 module length per second. Right. So these labels are provided by the creator of the library entry, the creator of the configuration of behavior, when they make it, and this is what actually makes up our library, right? So we can think of the library as basically a big matrix of configurations and behaviors labeled with properties. And what we can do then is if we, later when we're specifying, a task, we can specify, some sort of abstract functionality that we want in terms of properties, and have our high-level planner kind of index into this library and retrieve configurations and behaviors that satisfy that requirement. So for example, if we wanted a robot that can drive on sloped terrain, we'd see that these 3 entries all satisfy that requirement, right? So once the library's been created and a user comes along and wants to actually complete a task with the robot, they interact with our high-level mission planner, which is an existing tool from Professor Kreskazit's group called LittleMa. And again, Jim Ching did a lot of really good work on this tool. So basically what this allows you to do is specify your task, as I said, in kind of an abstract way in terms of desired outcomes and the constraints of the environment using properties. You can specify your task in structured English, which is kind of like natural language, kind of like regular English, except that you're only allowed to make certain kinds of logical constructions, right? So an example task specification might be, if you're sensing cup, then do push, visit location 1, visit location 2. So in this case, push is a behavior property. So we're not saying exactly what pushing behavior or what configuration we want to do this. We're just saying that we want anything that matches that property, right, in the library. So what LittleMop does is take this spec, turn it into linear temporal logic, which is then compiled down into a finite state machine controller that basically uses entries from the library that can be directly executed to control the robot to execute those behaviors and perhaps even switch configurations to complete the task. So to kind of zoom out and put all of this together, right? Users create library entries in vSpark, configurations and behaviors, provide labels for properties. This becomes our library. Then, when we want to complete a task, we provide high-level task specification in structured English to LittleMop, our high-level mission planner, which will then compile that down into a finite state machine controller, which can be executed to reactively control the robot to complete the task. So let's see how this works. Returning to our example scenario, we want the robot to move a waste bin next to the table, then climb up and explore the table. If it senses trash, push it off the table, and if it senses a cup, notify the user. So in order to move the trash can next to the table, the high-level planner selects this swerve driver configuration because it's able to actually drive under this trash can, which is kind of up on 4 legs, so it can't be pushed from the side, and pick it up and actually move it next to the table. So after that's done, it's going to drive over to the side of the table and prepare to reconfigure into another configuration that can actually climb up on top of the table. Okay, so to climb up on top of the table, the high-level planner selects this 7-module snake configuration, which is able to do the climb up behavior that we actually saw as an example earlier. And that's able to get it to lift its head up on top of the table. So it also needs to explore around, kind of roam around on top of the table and explore. And the snake's too large to do that, so it chooses to reconfigure by popping off the front module, which is able to execute a driving behavior, back up and spin to indicate that it's found the coffee cup. And now, when it explores this other region, it's going to find this piece of trash and push it off the table. Now it's going to return back to the body of the snake and hopefully stick to land. Okay. So we've seen that this framework is pretty powerful, right? We can specify tasks in a kind of abstract way, and we can encode the functionality, a wide variety of functionality of the robot in the library, and we can accomplish tasks this way. But of course, this system is only as powerful as the library, right? That's what encodes everything that you can do with the robot. And as of right now, creation of library entries is manual, right? People have to do this. People have to create the configurations, the behaviors, and the labels. So it would be great if we could automate this a little bit, right? So perhaps one way we could actually automate this is by transferring behaviors between structurally similar designs that can actually have the same functionality. So let's suppose that in our library we have this grasper design already. We've already made a behavior for it that lets it kind of grab objects with its two arms. And we've just created this new walker design, and we think it's pretty great. Maybe we've created a walking behavior for it. But looking at this, we can see that, well, it's got these two legs, and they aren't, structurally they're not identical to the grasper, but they're pretty similar, right? So we could imagine that they could probably be used in just about the same way to execute a grasping behavior. So is there a way that we could actually, kind of formalize this and transfer the behavior from the grasper over to the walker? So in this project, that's actually what we've done. This is a collaboration between myself and Mark and Yanis Monserratos and Sanjeev Khanna in the Penn CIS department. So we formalized this kind of intuitive notion in terms of this concept that we call design embedding. Right? So the intuition behind design embedding is if we have a design A and a design B, A embeds B if we can replicate B's joints using a subset of A's joints, right? So basically we can, A subsumes the kinematic functionality of B. And we formalize this condition in terms of basically some criteria on the kinematics and the topology of the two configurations. And we find that actually for the walker and the grasper does indeed embed the grasper. So we can find a mapping of the grasper's joints onto the walker's joints. So in our framework, designs are represented as graphs with nodes representing rigid bodies and edges representing revolute joints connecting rigid bodies. So that means each module is actually a small graph of nodes and edges, and when we connect modules together to form configurations, we're creating larger graphs. So this was designed with modular robots in mind, but it's not necessarily limited to modular robots. It could be applied to basically any other robot or kinematic structure that conforms to that model, rigid bodies and revolute joints. So we actually have an algorithm that can detect embedding between two designs in quadratic time as long as the two designs are trees. So the reason we're limiting ourselves to tree topology designs is because actually this is kind of a related to a graph embedding problem, which are known to be NP-complete and take exponential time. So by limiting ourselves to trees, we're able to use dynamic programming and solve this very efficiently. And in fact, many useful designs for modular robots are basically tree topology or very close to it. So I'm not going to go into too much detail into the topology and kinematic conditions that we use to capture embedding, but I'll kind of touch on them briefly. So there are three topology conditions. The first is node-to-node correspondence. So basically for each rigid body in design B, we need a corresponding rigid body in design A that it maps to. We have edge-to-path correspondence. So for each joint in the embedded design, we need either a single joint or a path composed of several joints and rigid bodies in the embedding design in order to map to that. And the third is vertex disjointness of paths, which basically ensures that degrees of freedom that are independent in this embedded design remain independent in the embedding design. The kinematic condition looks a little complicated, but it's actually not. Basically, if a node B prime embeds a node B, rigid body B prime embeds a rigid body B, there needs to be a particular position and orientation for them relative to one another, such that each of B's joints can be mapped one-to-one to a joint that's incident on B prime, such that they are coincident and axis aligned. So it can basically perform the exact same kind of kinematic motions. So, as I said, our algorithm uses dynamic programming to solve for embedding between two designs efficiently. We basically work upwards from the leaves of the trees, solving embedding subproblems at each step, kind of filling a table full of solutions, and then once we reach the roots, we know whether the two designs whether an embeddability exists. And at each step, we're repeatedly solving bipartite matching and inverse kinematics problems. So when we run this algorithm on the grasper and the walker, as I mentioned, we do find that an embedding exists of the grasper into the walker. And once the algorithm finds that embedding, it actually returns a mapping of joints in the walker, joints in the grasper onto joints in the walker, allowing us to transfer the behavior directly over from the grasper to the walker. Okay, so now moving on to kind of my systems work in modular robot for autonomy of these systems. So the experiments that I showed you earlier, demonstrate that we can complete tasks in a reactive way with these robots. In other words, they are responding to things that they sense, but all the sensing is being done basically using an overhead camera, right, that's tracking these April tags attached to the modules. So it's not really autonomous. It's reactive, but it's not autonomous. And also, I told you at one point that the swerve driver reconfigured into the snake, but you didn't actually see that happen. And that's because we did that by hand, right? We're doing manual reconfiguration. So in this work, I'm collaborating again with Jim Jing and Hadass, as well as Jonathan Doddelin and Mark Campbell. Dr. Jonathan Doddelin, actually, they both beat me out the door, and they'll never let me forget it. So we've worked to actually make all of this autonomous and use onboard sensing with the robots. So importantly, this is actually the first system that can autonomously have modular robots reactively reconfigure in response to their environments, unknown environments, to complete tasks. And this is really important, right? Because for a modular robot system, you could make the argument that if the system can reconfigure but can't do so autonomously, isn't this just the same as a collection of robots, right? For the experiment before, couldn't we have just done that with one swerve driver-like robot and one snake-like robot? And the answer is yes, we could have, right? They didn't need to be reconfigurable per se. But if you have a system that can reconfigure in response to its environment, and actually do so with autonomy, you can do things that a traditional robot system cannot do. Right? You can imagine that we might have the robot first as a snake, go through a small hole, then come into a larger open space, turn into a car, and explore. That's something that you can't do with a car plus a snake, right? You actually need reconfiguration. So in order to achieve this, we're kind of expanding our block diagram here to include actual onboard sensors on the robot, perception tools that allow us to extract environment properties from the 3D data coming from the sensors, as well as autonomous reconfiguration that will let the high-level planner choose to actually change between configurations when it wants to. So as I mentioned, S'mores EP has no sensors on the actual modules that are being passed around that let it gather information about its environment. So we have to expand the hardware by introducing the sensor module shown here. So as you can see, this is quite a lot larger than one module, right? So we have to have one of these carried around by a cluster of several modules, and that does introduce some complications in terms of motion planning and that kind of thing. Inside the body of the sensor module is a battery and a single board computer. We're using an upboard. The battery provides about 45 minutes of runtime. Our primary sensor is this RGBD camera. It's an Astra Astra Pro camera, which is a great lightweight 3D sensor if you need one. This is doing the bulk of the sensing for our robot. This is getting point cloud data to do SLAM, object identification, as well as environment characterization. But then also up at the top of this long stem is this webcam, which is kind of small and light, and just looks down at a region right in front of the sensor module, a rectangle about 1 meter by 3/4 of a meter in dimensions. And this actually provides localization for any module that's within this area that has an April tag marker on it. And this is really nice. It's kind of like the robot is carrying its own little motion capture system with it. And this is kind of an innovation that we developed to enable faster and more robust reconfiguration as compared to a lot of past systems, because we've got really rich information about where the individual modules are within this area. So, of course, one of the most crucial factors in autonomy is kind of the perception component, right? And my collaborator, Dr. Jonathan Doddelin, has done a lot of great work to kind of build the perception tools that we use in this system. So we're doing SLAM, object identification, and navigation using a lot of kind of off-the-shelf tools, open source tools in ROS. We're using some prior work of Jonathan's to do waypoint selection, a next best view algorithm. And in order to actually extract environment properties from the 3D data that the robot is sensing, in order for the high-level planner to make decisions, right? We're using these classifiers that can distinguish between 4 different kinds of environments, 4 different environments with 4 different properties: free, tunnel, high, and stairs environments. We're basically using voxelized templates here, and we're only distinguishing between 4 environments, but of course this could be expanded to more different kinds of properties, and if you wanted to use a kind of more sophisticated classifier, you could plug in your favorite convolutional neural net here and everything should work just fine. So in terms of high-level planning, we're using the same framework that I presented previously. There's just a couple of kind of key differences that I'd like to highlight. The first is that we're using a much smaller library in the experiments you're going to see here. That's because we were using this large library before, 50 configurations, about 100 behaviors. This demonstrates that we can capture a broad range of functionality, right? But when we want to do things autonomously, the bar for robustness in terms of the behaviors that we're doing is much higher. So we ended up using a much smaller library with kind of rigorously vetted configurations and behaviors that are more kind of tolerant to disturbance and that kind of thing. Also, the task specifications for a lot of these tasks are pretty simple. It's just kind of a few, like 2 or 3 different statements that the user will provide. But what you'll see is that actually when the robot enters different environments and kind of senses what's there, its behavior will change in some cases dramatically. As it actually responds to what it's finding in order to complete the same task under different conditions. So in this first experiment, the robot's task is to explore this L-shaped office environment, find any brightly colored objects, and bring them to the drop-off zone. So the drop-off zone is over here, and there's 2 brightly colored objects here that it's going to eventually find and pick up. So the robot begins exploring without any prior knowledge of the environment. It's doing SLAM and characterizing what's around it, and it pretty quickly recognizes that there's this pink object over here, which it needs to retrieve. Looking at the environment around this pink object, it sees that it's between these 2 trash cans, so it's kind of a narrow gap, and it correctly classifies this as a tunnel-type environment, and recognizes that in its current configuration, this car, it's too wide to fit in there. It's not an appropriate configuration for this environment. So it's going to choose to reconfigure to a different morphology that's got kind of a long arm on the front that's suitable to reach in and grab this object in a tunnel environment. So you can see here that this is kind of the downward-facing webcam view. It's tracking these April tags, providing localization as the robot's reconfigured. Okay, so after it retrieves the object, it's going to pull it back out and then reconfigure back into a car, which it needs to do in order to execute the required driving behavior to maneuver and actually bring this object to the drop-off zone. Okay.
Tarik, in this example, was
Yes.
the decision to reassemble made autonomously, or was that pre-programmed?
It was made autonomously.
And can you explain why? I mean,
Yeah.
its proboscis, it could very likely have achieved the task, and what was the trigger to have the
Right.
reassignment of morphology?
Yeah, so the task specifically is it needs to do an exploration behavior until it finds an object, then needs to retrieve the object and bring the object, drive the object to the drop-off zone. So in order to do the retrieval behavior, kind of the pick-up behavior, it sees that in the tunnel environment it needs to use something that's narrow, but in order to do the second portion of the task, the drive it to the drop-off zone, it needs to use something that can execute a driving behavior, driving and turning, which the configuration with the arm cannot.
You couldn't push with the proboscis?
So we can push in a straight line with the proboscis, but it's not able to turn and maneuver, which is why it turns back into the car. Or, I mean, if you really tried, you could probably get it to turn, but at least in the library that it had access to, it was not labeled that it was able to turn. Yeah. Okay, so in the process of picking up that first object, it also saw that there's this brightly colored green sprite can over here in the corner, and it needs to go and retrieve this object as well. It sees that this sprite can is in a free environment. There's nothing around it. Of course, it got caught in the crack in the floor, so Jonathan had to reach down and free it, but pay no attention to the hand. So in this case, the task specification is identical, right? It's not using anything about the color of the objects to make its decision. If the positions of the objects had been switched, the behaviors would have been the same. It knows that in this case, the object is out in the open, so it doesn't need to reconfigure in order to retrieve it. It can use this original car configuration. Okay, so it has completed its mission. In these next two examples, the robot's going to help us mail this circuit board from Penn to Cornell. It's helping us with our collaboration. So the task specification is pretty simple. It begins with an object in its possession. It needs to explore until locating the drop-off zone marked in pink tape. In this case, it's a mailbox. And then it needs to deposit the object there. In this case, it sees that in front of the mailbox is a staircase obstacle, which it could not drive up in its original configuration. So it chooses to reconfigure to this snake configuration, which is able to actually climb the stairs and perform the drop-off behavior. Now it's going to come back down and reassemble. So now if you want to mail something, of course, the postman's not going to pick it up without postage, so the robot has to now put a postage stamp on the package that it's going to mail. So in this case, the high-level spec is exactly the same. It begins with an object in its possession, needs to deposit it at the drop-off point, which is again marked with pink. In this case, it starts as a car, and it sees that there's no obstacle in front of the drop-off location where it needs to put the stamp, but it is up high, so it can't actually get the stamp up there as the car, and it needs to reconfigure back into this ARM or proboscis configuration in order to actually execute the depositing motion. Yeah, so the behaviors that it has available to this configuration are can basically drive forward and backward, pick things up, or lift the arm up while driving straight forward. Okay. So that's actually the end of part one on modular reconfigurable systems. Now I'm going to talk a little bit about environment augmentation. So at the beginning, I presented environment augmentation as a kind of analog to reconfiguration, right? The robot reconfiguring its environment as opposed to itself. Another way that I'd like you to think about this is that the robot is installing its own infrastructure. And this is something that people are really good at, that we do all the time. So if I need to reach an object on a high shelf, I could attempt the task dynamically by jumping, right? But that's a little dangerous. So instead, I'll usually go get a step stool and put it next to the shelf, changing the environment in a way that makes it work for my capabilities, right? And I think that this is kind of an underexplored concept in robotics, and something that could actually be very exciting and powerful, because robots can actually be co-designed with the infrastructure that they're installing, right? We can make robots that are great at building things and also great at interacting with the things that they build. So I've started to explore this idea with S'mores EP, with my modular robots, by introducing these, what I call augmentation modules, or really just building blocks that the robot can use to create ramps and bridges that let it surmount obstacles. And it can create ramps and bridges of different sizes by using different numbers of building blocks. These blocks are specially designed to be easily manipulable by S'mores EP. They've got these metal squares on them which let the robots latch to them with their magnets. And they connect together using neodymium magnets and have rubber tracks and sidewalls that make it very easy for the robots to climb them without falling off. So in the work that I'm going to show you, this is again a collaboration with Jim, Jonathan, Hadass, Mark Campbell at Cornell. We're actually going to introduce this structure building capability into our existing framework for high-level autonomy with modular robots, and show that not only can we achieve a functional advantage by doing this, but we can also actually integrate it into our planning framework in a pretty elegant way. So you might ask the question, why do this with modular robots, right? Well, this actually addresses a pretty common scaling problem with modular robots. You might think that a modular system would be very scalable, right? If you want to address a task that's kind of on small length scales, you just use a few modules. If you need, to travel large distances or over large obstacles, you make a big robot using lots of modules, right? Easy. Well, it turns out that actually, you can make a big robot by adding more modules, but you're not making the robot any stronger, right? So if you're trying to make a really long arm or leg out of modules, the actuator strength of the module back at kind of the shoulder of your arm is remaining the same as you add more modules. So very quickly, you're going to overload those actuators, and the robot won't be able to move itself. So in fact, this example I showed you earlier of the snake climbing up to the top of the table, this is actually as high as S'more's EP can lift. If you try to go one module higher, the bottom module will actually torque out as it's trying to kind of lift this column of modules up to the top. Right? So this is a real problem for us. And in the past, one way that we've kind of addressed this as a field is by saying, okay, well, we'll use these robots in space, which is a great application, but we'd like to use them on Earth sometimes as well. So I see structure building as a potentially a very scalable alternative, right? You can have a small robot build a very, very large structure if it's got enough building blocks and time available. I should have changed this from the Empire State Building to the Samsung Building in New York, because that's where I'm working after this. But, don't tell Dan Lee. If we want to integrate this capability into our existing framework, of course we need some perception tools to go with it, right? So, Jonathan's done a great job of developing some probabilistic template-based, classifiers that basically will look at features in the 3D mapper on the robot and tell the robot whether that might be an augmentable piece of environment, right? So, for example, it'll look at the side of this drawer with some books in it and say, okay, this qualifies as a ledge of height 2. I'm detecting these features. That means you could put a ramp of height 2 there and maybe gain some advantage by doing this, right? In terms of high-level planning, we're actually able to integrate it into our framework in a fairly elegant way, right? So the high-level planner is now able to select environment augmentation as another kind of path, as opposed to reconfiguration if it needs to, change the nature of the task that it's trying to solve. And in addition to configurations and behaviors in our library, we now have a library of structures. And structures change the environment properties, right? So if we have a ledge of height 2, we can map that environment property to a ramp of height 2 by building a ramp at that ledge. So basically, this is what the library entry would look like, right? We've got an associated classifier for detecting ledges, a set of building blocks that we need to create the ramp that goes there, a recipe, which is basically a small task the robot could choose to execute in order to make the ramp, and then that actually takes a ledge environment and turns it to a ramp environment, which another configuration from the library might be able to climb. So let's see how this works. So in this case, the robot's task is very simple. It just needs to move from its start point to the goal marker in pink over here. Using its environment characterization tools, it sees that there's this gap between the tables here. And in fact, this gap is too wide for the robot in its current configuration or anything it could actually transform into to cross on its own. But it does see that environment feature is a candidate for environment augmentation. If it could build a bridge of length 3, it could place it across that gap and actually complete its task. So it looks around and sees that it does, in fact, have the correct building blocks available, chooses to construct the bridge, and then places it across the gap to complete its mission. So all the placement and detection here is being done autonomously with onboard sensing. Okay, so that's a pretty simple task, but we can solve more complicated tasks as well. In this case, the robot knows that this thing is a drawer, a set of drawers, because it's marked with this pink tape, which indicates that. And its task is to open the bottom 2 drawers and look inside to try to find some missing objects. Well, opening the bottom drawer is pretty easy. It latches to it with its magnets and pulls it out. But it sees that in order to open that second drawer, it needs to climb on top of the first drawer, which is full of books. So this is a ledge of height 2. It's, environment characterization tools tell it that. It knows that it can't climb it on its own, but it does know that if only it had a ramp of height 2 available to it, it could put it there and make its task feasible. And conveniently, someone has left a ramp of height 2 lying around next to the drawer, which makes the robot's life a little easier. So it's going to send these 3 modules up and open that second drawer to find the missing objects. So this is actually being done reactively. It's not pre-scripted. It's actually reactive, task controller. If that drawer was empty. There's another video I won't show you where the first drawer was empty, so the robot could not climb on it. It knows that its mission is infeasible, and it gives up. Okay, so we've seen that environment augmentation can be useful for tasks, and that we can actually integrate it into our existing planning framework, which is great. But the way that we were kind of selecting what structure to build was entirely discrete and library-based, right? We need these individual library entries for individual structures. If you want to build a ramp of height 2, you need a classifier for that, and you need a library entry. Same thing for ramp of height 3, ramp of height 4, and so on. A more kind of scalable approach that we might be able to kind of add into this system is, if we had some theory that allowed us to determine, given an environment, could we actually look at the properties of that environment and the traversal capabilities of a robot and directly synthesize necessary structures from those constraints? And that's actually what we've done in this work. So this is some theoretical work. It's a collaboration with Cindy as well as Colin McCloskey, who's a very talented undergrad from Yale who worked with me this summer. So specifically, the problem we're trying to solve is, given an environment, a robot, and a set of building blocks, can we find a min-cost set of structures, in other words, a structure that uses the fewest number of building blocks, that we could add to this environment to make the entire thing reachable by the robot, the entire environment accessible to the robot? So, in our formulation, we represent the world as a height field, so kind of 2.5D. This is an XY grid of cells with an associated Z height at every grid. And we represent the robot's capabilities in terms of this local traversability condition, which is basically a maximum local slope and maximum discontinuity the robot can successfully traverse. So using this traversability condition, we can look at the height field and kind of turn it into a graph where nodes represent cells in the height field and edges represent valid transitions between cells that the robot could make. So if you imagine a small robot like S'mores in an environment with kind of relatively large objects like the tables and chairs around here, many of these regions are going to be inaccessible to the robot because they're too much of a slope, too high of a discontinuity, and therefore we're going to have many different connected components in our graph. So we call these regions, these connected components of the graph. And our goal is to introduce structures into this world that actually make the world fully connected, right? Make this graph fully connected, fully traversable to the robot, and use the fewest number of building blocks. The structures need to be ramp-like, in other words, supported from underneath. So we're not considering bridges yet, although we probably could in the future. They're made of discrete building blocks, like the ones that I showed you earlier. Actually, I forgot that I have them here, so you can pass these around too. And one crucial point about them, actually, if I have them back for a second. These building blocks have these kind of side walls, so that means that you can't actually make a structure that looks like this, right? They need to be kind of straight lines, and that's actually very important to our formulation here. So, so the structure.
Actually, show me.
Sorry, what was that?
She didn't
Margin
see.
five
Oh,
camera.
sorry. Okay, so these are our building blocks, right?
Yes,
So they have these side walls, right? So that means that you can't build a structure like this, right? It has to be like this. So the blocks need to all be in one line. Yeah.
Thanks.
Sure. So other than that, we can put them in any location in the environment. They're not constrained to the grid. They can be basically arbitrary position in SE2. Our algorithm that solves this basically has two steps. First, we're going to enumerate the full set of potentially useful structures that could be introduced in this environment. And then among them, we're going to find kind of a minimum spanning tree of structures that spans this entire set of regions. So to enumerate all the useful structures, we can place them at any point in the environment, but we're taking advantage of the fact that we know that for a structure to be useful, it needs to build a bridge between two disconnected regions, right? So that means that they really need to lie on the perimeter of regions in order to be useful to us. Because they are in straight lines, and because basically the traversability condition means that in order for the robot to move from the structure to the region, it needs to be fairly perpendicular to the boundary. What we're trying to do then is basically shoot out structures along the entire perimeter of each region, normal to the region boundary. So at a kind of discretized set of points along the perimeter, we'll try to solve for an optimal structure at each of these points by solving basically a 2D constraint satisfaction problem imposed by the traversability condition that models the capabilities of the robot. So basically, if we start at the top of a cliff like this here, we have this kind of cone or triangle of accessible area to which we could connect with a structure that is traversable. And we basically just try to build a structure to the first piece of ground that we find that falls within that accessible area. So in this case, the structure looks like this. And we actually have we prove that we only need to consider this kind of smallest structure we can build at this point. Any other structure we could potentially build there is in a sense redundant. So by doing this at every point along the perimeter of each region, we actually enumerate, at least up to our discretization, all the potentially useful structures that we could maybe build in this environment to help the robot. So once we've got this big set of structures, we abstract the problem up to a new graph where nodes represent regions and edges represent structures connecting regions. And basically what we're trying to do is compute the minimum spanning tree of this graph, which is easy, right? Except that it's not in this case, because structures are physical objects, and this introduces some conflict constraints which actually make the problem much harder. So if you imagine if we've got a structure here that's coming out from the seat of the chair, this is the height field for that table interior environment at the beginning example, and another one coming out this way, these two structures intersect, so we couldn't use them at the same time. They would conflict with one another. Another kind of slightly more subtle conflict exists when you have a structure that cuts all the way across a region. So in this case, this structure goes from the tabletop to the top of the chair, cutting all the way across the seat of the chair, and it divides it into two regions. Right? This is no longer mutually accessible from within the region. So we need to treat that region as two regions if we want to use that structure. It turns out that once you introduce these kinds of constraints, they are specifically pairwise binary disjunctive constraints. You can show that this makes the minimum spanning tree problem NP hard. And actually, in the worst case, it will take time exponential in the number of conflicts. Fortunately, in practice, we are able to solve this problem reasonably efficiently with kind of practical speed in realistic environments by employing branch and bound. So, in the worst case, it's still exponential, but kind of the intuition here is that it's exponential in the number of conflicts, and there are usually, for most real environments, a lot more kind of feasible ways you can use structures that are not conflicting than structures that are conflicting. And by kind of intelligently structuring your search through the solution space, you can find a good solution, actually an optimal solution, pretty quickly. So this is exactly what branch and bound does. This is a common method for solving combinatorial optimization problems. It's an intelligently structured search of the space that actually prunes out a lot of the search space. Basically, the way we do this is first we just use Kruskal's algorithm to find the minimum spanning tree without respect to constraints at all. This runs very fast. If the solution has a conflict, we branch the problem, forming two new child problems, in which we basically remove one member of the conflict set in each child problem, and then we show that actually by recursively solving these problems and returning the cheapest child solution, that is actually the optimal solution to the parent problem. We're able to prune a lot of branches in this search if the cost of the minimum spanning tree is more than the best yet solution that's been found. We're able to do this because we prove that actually the cost of the parent solution without respect to conflicts is a strict lower bound on the cost of any feasible child solution. So we can actually ignore any branches that are cost more than our current best solution. So in practice, this explores only a tiny fraction of the potentially very large solution space, and we can solve typical indoor environments in about a minute. So for example, in this kind of table and chair example, we generate 634 structures in about 6 seconds. We explore 33 branches in the branch and bound, 33 tries of the minimum spanning tree, and solve the entire thing in about 21 seconds. One thing that's kind of interesting about this solution is it actually includes this structure that does go all the way across this region, right? It goes all the way across the seat of the chair. The algorithm chooses to put this all the way over at the side so that it doesn't actually split that region into two. If it had split it into two, we would need one more structure and it would be a more expensive solution. If we make a small change to this input environment, pushing the chair in, now there's no longer enough room to build on the seat of the chair, and the algorithm is forced to select this much more expensive solution using actually 46 building blocks instead of 17 in the solution before. So actually finding optimal solutions here is functionally useful, right? It would take a lot longer to build this than the solution before, and this is a feasible solution for the previous problem. We're able to do this using real data from real environments as well. Colin this summer helped me a lot actually gathering data and processing the 3D data in order to make it useful for our algorithm. So this is a scan of some objects that you might recognize if you work in Perch. And this solution is found in about 1 minute. That includes all the data pre-processing time and that kind of thing. And we see that actually by introducing these structures on this environment, it does make the whole thing accessible to s'mores. All right, and we have another example. This is a staircase from the first floor of the Pennovation Center. The algorithm selects these 5 2-module high ramps to add to this environment to make it traversable. You'll notice that the placement of the ramps seems kind of haphazard, and that's because, with respect to the cost function that the algorithm is using, the actual placement of the ramps doesn't matter. All it cares is that it's connecting the entire environment, right? So it's not taking robot path planning into account here. Nevertheless, the robot is able to actually climb all of these ramps and reach every step. So in the future, we could perhaps take a robot path planning into account here, and maybe post-process the actual positions of the structures in the environment to minimize path distance for the robot, that kind of thing. Okay, so that's actually the end of my talk. Thank you all for coming. I just want to take a minute to thank all of my excellent collaborators in this work. I've been very, very fortunate to work with a number of really talented people. In particular, the doctors Jim Jing and Jonathan Donnellan have spent many a very long night with me running autonomous robot demos. So I really want to thank them for their work. If they're hopefully out there watching on the live stream. Yanis Monserratos worked with me on the embedding, design embedding work. And I've also been very fortunate to work with excellent faculty at Penn and Cornell as well. And last but not least, I want to give a big shout out to the s'mores EP team. So I didn't actually get to talk about the robot itself that much, but building that robot was a titanic effort of many people. Certainly not just me. The people that you see here, as well as some others that I couldn't fit on the slide. Really without all of their effort and talent, none of the work you see here would have been possible. So thank you very much. Of course, all my lab mates in Mod Lab and Mark. Thank you as well. So I hope we have a little time for questions. I know I went a little over time. Apologize for that. But,
Questions from the audience?
sure.
When the little car or little map went
Yeah.
into that room, decided to go under the table and lift it, how did it know it should lift rather than just push? You said
Right.
it knows that it can push it.
Yeah, so in that case, like I said, that was reactive but not autonomous, right? So the robot is not, really sensing what's around it, but it's basically gathering information from the April tags, those kind of black and white markers that were placed on everything. So that trash can had a black and white marker on it, and when the camera that's overhead sees that, it knows that is a trash can that has certain properties. One of which is that it's up on legs, so it can't be pushed from someone from the side. Yeah. So we're kind of spoofing the sensor information in that case. In the later work, we would have had to.
We're using the sensor.
Yeah, we're using the sensor on the robot. Yeah. Turner.
So similar vein of question. So in the task where it decided, the high-level task was to go find the shiny objects, but the
Yeah.
first one's in the tunnel. Is it evaluating some metric of closeness of the tunnel, or does it do a classification and decide this is a tunnel and therefore there's a proboscis behavior for it? How
Yeah.
does that kind of interpret?
Yeah, right. So for that work, basically there are four kinds of environment properties that we consider, right? We have a classifier that can classify each of those 4 properties, right? So one is free, one is tunnel, one is high, and one is stairs. So the robot is continuously running that classifier, pretty purpose-built classifier on all the 3D data it receives in the vicinity of objects specifically. And then once, when a given classifier goes off and says, okay, this counts as a tunnel, that's labeled with that property. And then that property then allows the high-level planner to index into the library and find configurations and behaviors that can operate in a tunnel environment. Yeah. Yeah, so basically, each behavior in the library is labeled with properties, right? So for example, the lifting up behavior for the swerve driver is kind of labeled with properties that describe, okay, so this is called lift up, which is, doesn't actually encode anything physical, but has to have kind of a common meaning among the creator of the behavior and the user of the system, right? And then we'll be labeled with things like, this can lift objects from beneath, between these heights, that kind of thing. So then in terms of actually extracting that data from the environment, in that case, that was just all being encoded by what April tag was on the thing. Right? So the system sees that April tag, it knows, okay, that's a trash can, it's in that location, it's got all of these properties that it needs to know. So in that case, we weren't doing any real sensing, it was just kind of smooth.
I think it's really interesting to basically using to modify the environment in order to go to your goal. But practically, I think it'll be quite troublesome in order to either carry a lot of building material or to find appropriate material in the environment. So
Definitely.
do you think in the future it's possible to use part of the robot since it can shifting to build a certain path to basically integrate or attach to the environment? To build a path so that it can later also reattach to the robot itself.
Yeah, definitely. So that's a great point, right? So indeed, certainly it would be pretty time consuming and difficult for the robot to bring all of its own building materials in if they looked like the blocks that are circulating around. I think that this environment augmentation is kind of an exciting idea and something that I'd like to take further. And in the future, I think it would be interesting to think about, co-designing the robot and the structure in a more real way, right? So in this case, S'mores was built, and then I built the building blocks afterwards as kind of a retrofit. I think if you kind of were thinking about the system from this perspective at the beginning, it's a really interesting design problem, right? You could think about having very compact building materials, maybe pop-up building materials or something that the robot could carry with it. Pop-up building materials. That the robot could carry with it, right, in order to create structures and have it be a little bit easier to carry around. Yeah. What was that?
Or just split the modules on the diagonal, have two modules that are split on the diagonal.
Yeah, I mean, so you could also think about actually using the, you mean the blocks on the diagram? Yeah, I guess that's a possibility as well. So like Feifei was saying, you could also think about using the robot itself as structure. Oh, I see, okay. Yeah, so you can do that, and actually other people have done that before. There's a lot of kind of lattice-style modular robot systems. M-Blocks is an example of a system like this. I think that that's a good strategy, but of course, if you're having the building material be robotic, it's going to be more expensive, to kind of make and harder to make more of. Yeah. Alec?
So the behaviors that you described in the first part, we're treating them pretty kind of discrete and symbolically.
Yeah.
But they seem to be quite, much more rich in the sense that some of them can drive, some of them appear to have non-autonomic constraints.
Right.
I wonder how you represent those in your matrix that you described.
Yeah.
The second part of the question is, in this matrix configuration, or the behavior configuration matrix that you described, that's a very interesting idea to me, and I was just wondering if something like that, you'd rather it be sparse or dense in the kind of the work that you're doing.
Yeah. No, those are really good questions. So the first question, I kind of, so some of the behaviors, we are actually treating them all as kind of discrete entries labeled with these properties, right? Everything's sort of discrete. But some of them are actually a lot more kind of rich than others, right? So especially in the first work, most of the behaviors were pretty much open loop. In the autonomous stuff, some of the behaviors are parametric, right? So they actually take in a parameter as input. For example, a driving behavior can take a heading angle and velocity, and that actually allows us to do a lot more with them. So what we'll have is kind of in some cases a feedback controller that's actually taking in sensor information, doing some low-level control, but it's all wrapped up in a library entry that's still treated as discrete, described with properties and these kinds of things. So in terms of library design, I think that's a really, really good question and still an open question for us, right? I think that you could certainly imagine perhaps a kind of big data approach where you just generate as much stuff as you can and label it any way that you can. But now, of course, you've got a lot of configurations and behaviors, and how do you ensure that the properties that you're labeling them with kind of match up between the user's understanding and the designer's understanding and all this. I think that one thing that would be really interesting to think about is whether there's maybe even sort of a spanning set of configurations and behaviors that we could think about for the library. Right? Is there like a minimal set that we could come up with that we can prove is at least rich with respect to a space of tasks? So that's something that I've thought about a little bit, but it's a really hard problem, right? So that's yeah, very interesting question. Yeah, somebody else's PhD. Gosh.
I have a quick question for implementational detail.
Yeah.
The last video that you showed, for the robot climbing 5 steps.
Yeah.
How are you doing the localization for that?
Oh, that's all teleoperated. Yeah,
I was gonna
fully
ask-
teleoperated. So my undergrad Colin is not only a great computer scientist, but also a great robot driver. So he did a good job with that.
Okay.
All right,
All right.
so should we, so everybody who is not Penn faculty, it should leave the room, and
4:30 and 5:08 is your catch.
Yeah.
you're welcome to stay if you
Sorry.
want.
Yeah. So thanks. Thanks, Jack. Thank you. Yeah, I'll definitely. All right. Well, they're actually going to take the donuts, so if you guys, I could have them leave a box if you guys want some donuts.
Yeah, do you guys want?
Fancy donuts?
Okay.
What?
Hadas wants it.
We have donuts here. I seriously considered having donuts delivered to your office, but I figured I wouldn't know how to have them actually come into the building.
No, I was wondering if it's the fancy donuts.
Yeah, it's actually even fancier donuts.
Whoa.
Yeah, so it used to be Federal Donuts, now it's Bueller's Donuts, which are even better. So
Okay, next time I'm in Philly, you tell me
I
if you
think
don't.
so.
I'm not trying to.
They're very, very good.
Had the federal.
All right.
All
Anybody
right,
else?
so should we close the door?
Sure. Yeah.
So we are now in the committee questioning part of the defense. Anybody who has questions for Tarik should feel free to bring them up. Would you like to start, Hadas?
Yeah.
I'll,
Can you turn it down a little bit?
Sorry. Oh yeah. So we can.
Timbers.
Oh, actually, I need to stop the live stream. That's important.